Bismillahirrahmanirrahim. Today we are going to discuss fifth lecture of our subject topological indices of chemical graphs. This is the outline of our today's lecture. First we will discuss about graph operation and the degrees of vertices in graph operation and some other properties of this operation, and we also calculate or investigate the formulas of degree based topological indices of some graph operations. So first let's discuss what are the graph operations. Graph operations are useful to construct or used to construct new graphs from initial ones. There are two major types of graph operations. One are the unary operations and the other are the binary operation. In unary operation we use usually one graph to obtain a new graph by applying some operation, while in binary operation we use two graphs to construct or develop a new graph. Another beautiful use of graph operation is that complex networks can be generated with the help of some basic graphs, and the properties of these complex structures can be studied with the help of the properties of the basic graphs. So like numbers we add or we can like numbers that we can add or subtract two numbers and we obtain a new number. Similarly in graph operations we can apply some operations on graphs to obtain new ones. So let's move and see some in our next slide some unary and binary graph operations. First two, I mean the vertex deletion and edge deletion, are the very basic operations which we will discuss, and some binary operations are also discussed in this lecture. So let's start with some very basic graph operation, which is a vertex deletion in a graph. For a graph, let G be a graph and V is a vertex of a graph G. The graph obtained by deleting the vertex V and its incident edges from G is denoted by G minus V. I mean in vertex deletion we set or we choose a vertex and delete that vertex and along with its incident edges. Here is an example. Here we have a graph G. You can see that we choose the vertex V, and when we remove vertex V, the vertex V and its edges are also removed. So this is our graph G minus V. Some properties like the order of the graph G minus V is one less than the order of the graph, and the size is of the graph G minus V is size of the original graph G minus degree of the vertex V, because we also removed the number of edges which are incident with the vertex V. Further, if we see the degree behavior of vertices in the graph G minus V, if vertex U is incident if the vertex U is adjacent with vertex V, then the degree will be degree of G minus 1 less than the original one, and if it is not adjacent with the vertex V, the degree will remain same. So these are some basic properties of vertex deletion graph. Next we have similar lines, edge deletion graph. Let G be a graph and E be an edge of that graph. The graph obtained by deleting the edge E from G is denoted by G minus E. Similarly, as we did in our previous slide, the edge deletion we set or we choose an edge and delete the edge. You can see this is the graph G and this is the graph G minus E. We have no restriction. We can delete any graph up to our necessity. And now we discuss some properties. You can see from the example the order of the graph G minus E and the order of the graph G is similar. As we removed one edge, so the order remove only one edge, so the size of the graph G minus is one less than the size of the original graph. And similar we have, if the vertex V is incident with edge E, then the degree is one less than of the original one, and if the vertex u is not incident with the edge e, the degree will remain same. This property can be easily checked from the above examples. So here is a very easy exercise for you. Investigate the first and second Zagreb indices for vertex and edge related graphs. Only you just have to remember the or recall the formula of the first and second Zagreb indices, and just you put the values of these vertices of degrees in the formula of the Zagreb indexes and Zagreb indices. So remember, this is a very important in today's lecture. I mean the degree based, because we are talking about the degree based topological indices. So this a property, the or the degrees of the vertices in the new graph is very important. So in our next slide we will discuss some graph operation, their properties, and we will investigate some topological indices. So here is an exercise, please you must try this. So start with another graph operation is a complement of a graph. This is a unary graph operation. The definition is of the complement of a graph. The complement or inverse of a graph G is a graph G bar. On the same vertices, you can see that same vertices mean the order will remain same, such that two distinct vertices of G bar G bar are adjacent if and only if they are not adjacent in G. From definition you can see that two vertices, if they have an edge in G, they do not have edge in G bar. And next, vice versa, you can see that is to generate the complement of a graph, one fills in all the missing edges required to form a complete graph and removes all the edges that are previously there, or in simple word you can say that you have to remove the previous one and draw the graph which are non-adjacent, draw the edge between two vertices which are non-adjacent in G. Here is an example. We can see that here we have a G. This is a procedure of complement. You can see that there is no edge between the vertex V and between the vertex U in graph G, but in complement you can see there is an edge. Similarly, if this is W or this is X, you can see there is no edge between W and X, but in complement you can see there is N. So similarly we draw the complement of a graph which is like this. So now let's see some properties of complement of a graph. Let G be a graph of order n, then the order of a graph G complement and the order of the graph G is same, which is n, and the size of the complement of a graph is n into n minus 1 divided by 2 minus size of the graph G. Similarly, the degree in the complement of a graph V is equal to n minus 1 minus degree of V in G. Let's just discuss about this, how we get this result. Suppose we are in a graph G. Here this is our G, you can see, and the order is of the graph is n, order is n. If in this graph the vertex V has degree 3, in complement, according to definition, this V must be adjacent to the other n minus 4 vertices. So because here degree is 3, this is adjacent with these 3 vertices. In complement, according to definition, V must be adjacent to the non-adjacent vertices in G. So the degree must be like, in general way, n minus 1 minus degree of V. Here if degree is 4, then this will be 5. आप कह सकते हैं, आप देख सकते हैं कि अगर हमारे पास डिग्री जो है वो 4 है या 5 है या 6 है, तो इसका मतलब है कि वर्टेक्स वी जो है वो 6 वर्टिसेस के साथ एडसेंट है, और इसने कॉम्प्लीमेंट में बाकी जो वर्टिसेस हैं उनके साथ अटैच होना है, उनके साथ एडसेंट होना है, और जो इस वक्त जिनके साथ वो जी में अटैच है उनके साथ एडसेंट नहीं होना है। इसलिए हमने जो जी कॉम्प्लीमेंट है उसका एक जनरल फार्मूला हमने यहाँ पे ड्राइव कर लिया है। ये फार्मूला जिसे मैंने पहले बताया इंपॉर्टेंट है, क्योंकि हम बात करेंगे डिग्री बेस्ड टोपोलॉजिकल इंडिसेस की। सो प्लीज रिमेंबर दिस फार्मूला बिकॉज वी आर गोइंग टू यूज दिस फार्मूला इन our next slides to compute some topological indices of complement of a graph. So our first question is the first Zagreb index of the complement of a graph G. From the definition of the Zagreb index, we have the here we have any graph G. We have to sum up, we have to scale the degrees of the vertices and sum up all the values, which is the first Zagreb index. So this is the definition of first Zagreb index. Next, as we know, in complement of a graph, the vertex set of the complement graph and vertex set of the original graph G remains same. So we can replace G bar by G. Here we have a formula, as we discussed in the previous slide, that degree of V in complement of a graph is equal to n minus 1 minus degree of V in G, and this scale is of the formula. So this is first step. ये हमारा पहला स्टेप होगा। यहाँ पे जस्ट हमने जी कॉम्प्लीमेंट को रिप्लेस किया है जी से, और यहाँ पे हमने जस्ट वैल्यू पुट की है, हमारे पास इस टर्म के हमने वैल्यू जो है वो रिप्लेस की है। फर्दर जस्ट वी हैव टू expand this scale and apply the summation. Like if we consider this is A, this is our B, you can see that A square plus B square minus 2AB. So first, next we apply this summation. This gives this expression because there is no V involved in this term. So n minus 1 whole square is a constant. Here we have n terms, so this n is multiplied by this one, and this when we apply summation here, this gives the first Zagreb index of G. Further 2 into n minus 1 comes up here as it is, but when we apply summation here, we apply here handshaking lemma. The handshaking lemma is a very famous one, which is the first result of any graph theory book. So this is our first result, or you can say this is the final formula for the first Zagreb index of complement of a graph. So next we have the second Zagreb index of the complement of a graph. Remember the formula of the degree. So start by definition. This is the definition of the second Zagreb index. Apply the formula of degrees here. For U and V we have like this one. Further, if further we have some computation, we multiply these terms and we obtain this expression. And by definition we know that if two vertices are adjacent in G complement, they are non-adjacent in G. So we replace this term by this term. After that we apply this summation on each term. Here we obtain, when we apply here, we got n minus 1 whole square is a constant term, but I think there is some mistake. There will be n into n minus 1 divided by 2, I mean complete graph, minus, you can say that the order or size of the graph which are not which are not edges in G complement. Further we apply summation. Next, this is a constant, again constant as it is. When we apply summation here, we got first Zagreb coincidence graph, and when we apply summation here, we get second coincidence Zagreb index here. So this is the formula for second Zagreb index of the complement of a graph. Some exercises. Find the formula for the forgotten index of a complement of a graph. Further, the first reformulated Zagreb index of complement of a graph. These two are exercise. You can do these exercise for your practice. Next operation is our K-subdivision of a graph. For a graph G, a graph obtained by inserting a new vertex in each edge of G is called the subdivision graph of G and is denoted by SKG. Sorry, here is not SKG, here will be only SKG. If we insert a vertex on each edge, a unique vertex in each edge, this is called a subdivision of a graph. When we talk about the K subdivision of a graph, we insert K new vertices in each edge of a graph. The subdivision of a graph of the graph G and the K subdivision graph is denoted as like this. So here we have example. I mean, if I remove this, this is our graph G, and we want to do its two subdivision graph of G is obtained by replacing each edge by, you can see here, by inserting two new vertices. So this is called the two subdivision graph of G. So next, some properties of K subdivision of a graph. The first we notice the order of the K subdivision graph is order of the graph G plus K times the size of the graph G. Next we have the size of the K subdivision graph of G is equal to K plus 1 times size of the graph G. And next our important result or important property, the degree of any vertex in K subdivision graph is given as if U belong to vertex set of G, then degree will remain same, and otherwise if U is a new vertex, its degree will be 2. If we move to the previous slide, you can see here the red vertices are the new, and each new vertex has degree 2, while the black one the old vertices, and the black vertices has same degree as they are in graph G. So this is our result for degree of vertices in K subdivision of graph. Now we investigate the second Zagreb index of K subdivision of a graph G. This is the definition of the second Zagreb index. From the definition, we observe that each edge, there are two types of edges. One type of edge is whose one vertex is from V and whose other vertex is from V dash, where V dash is a set of new vertices which we inserted on each edge. So each edge which is whose one end from V and other end is from the new vertex is treated here, while if both ends belong to the new vertices will be treated here. So there are only two types of edges here. By the formula of the degree, you can see if V belong to the vertex set, the degree will remain same. I come here like this, and if it is a new vertex, the degree will be here 2. So here degree of V in G multiply by 2 for first type of edges. For second type of edges, let's see what happen. You can see both end vertices are from the new vertices are the new vertices, and for new vertices the degree of new vertices are 2. And when we simplify this expression, this gives 4 times number of edges in a graph G, and when we simplify this gives the 4 into K minus 1 into size of the graph G. So this is the final expression for the second Zagreb index of K subdivision of a graph. Some more exercises for K subdivision of a graph. Investigate the hyper Zagreb index of 3 subdivision of a graph. In 3 subdivision of a graph, you have to insert 3 vertices in each edge. And next exercise is investigate the first multiplicative Zagreb index of K subdivision of a graph. And furthermore, if you do not remember or do not know any definition of the topological index, you can comment or you can search it on Google, because there are hundreds of topological indices which are introduced up to till date. So maybe it is difficult for us to discuss all the topological indices. By the way, anyway, you can ask in comment about the definition about your queries. Further, you can search on Google for any definition. So next we have an example line graph of a graph. For a graph G, the line graph denoted by LG, the line graph of a graph G can be obtained or can be achieved by converting the edge. So please first note that in line graph, to generate line graph, convert each edge of G into a vertex, each edge of G into a vertex, and now the adjacency, two vertices are adjacent if and only if the corresponding edges are adjacent. This is the definition. So now we try to explain this by an example. Here we have a graph W4 and we want to convert this W4 into a line graph. According to definition, we insert it or we replace each edge, each edge by vertices. You can see that we draw vertices on each edge. Now when two vertices are adjacent, you can see according to definition, two vertices are adjacent if their corresponding edges are incident, are adjacent, sorry. So you can see these vertices are adjacent because their corresponding edges are adjacent. Here we have a little mistake, we correct it here. There must be an edge and there must be an edge, because these two edges are adjacent and these two edges are adjacent. That's why we draw these lines here. So after applying these definition on all vertices, we get this graph, which is line graph of W4. So next we move to the next some properties. Further, we have the order of the line graph of G is equal to size of the graph G, because for corresponding to each edge we have a vertex in line graph. The size of the graph or the size of the line graph is given as summation degree of U, of course, for each vertex, degree of U in G into degree of U minus 1 divided by 2. You can check this from the definition and by taking some examples. And first, next the important result for us. Let W be a vertex corresponding to UV in LG. UV is a vertex, is an edge in G, and W is a corresponding vertex in line graph of G. Then sorry, here is a typo mistake. The degree of W in line graph of G is equal to degree of U plus degree of V minus 2. So this is the formula for vertices, degree of vertices in line graph of G, and this formula is directly from the definition of the graph. So we will use and apply this formula to compute some degree based topological indices of line graph of a graph G. So start from the first Zagreb index. This is the definition. You can see after that we apply or use the formula of the degree of the vertex. Here we convert summation. You can see W belong to the vertex set of line graph of G, and we know that according to definition, for each vertex of line graph, we have a corresponding edge in G. So we replace W by UV, an edge in G, and here we put the value of the degree of the vertex W. After that, just we have some simple computation. Apply the formula like you can see A, B and C. A square B square plus C square plus 2AB minus K2AC. After that we apply the summation. When we apply the summation, these terms both give us the forgotten index. This is a constant. The summation is on edge sets. Remember that the summation is on edge sets. So when 4 is a constant, so here we have number of edges And you can see that when we apply summation here, this is the definition of the second Zagreb index, 2 into second Zagreb index. And here you can see I remove some lines here. When we will apply the summation here, this is the first Zagreb index, so minus 4 into m1 of g. So this is the generalized formula for first Zagreb index of line graph of any graph, of course. First Zagreb index of line graph of a graph G. What is this? Look this. Furthermore, from equation 1, notice that, okay, first we see what is equation 1. Yes, this is equation 1. Yes, here from here equation 1 we have a good observation that if we notice that this is exactly the definition of first reformulated Zagreb index. So we can see that first Zagreb index is of line graph of G is equal to the first reformulated Zagreb index of graph G. So here we have this result also. Some exercise for your practice: examine the first and second multiplicative Zagreb indices of the line graph of a graph, of course any arbitrary graph G. So move to the next slide. Yes, this is our first binary operation. Before this we will talking about the unary operations, and this is our first binary operation which are going to discuss. So sum or join of two graphs, let G1 and G2 be two graphs on disjoint vertex sets. Their sum is the graph G1 plus G2. This is the notation of sum of two graphs, and the vertex set of G1 plus G2 is union of both vertices, the vertex set of both graphs. And the edge set will be obtained all the edges of G1 union all the edges of G2 union each vertex of G1 is adjacent with each vertex of G2. remember here G के हर vertex ने G1 के हर vertex ने G2 के हर vertex से edge बनाना है. So this is the complete edge set of join of two graphs. Okay, so now let's try to understand the join of two graphs by an example. Here we have G1. If I change color to red, G1, you can see here this is G1, this is our graph G2, and we will want to find the sum or join of these two graphs. So these two graphs, here we can see here this is G1, this is G2. both the graph are taken as it is. हमने दोनों ग्राफ्स को as it is लेना है. उसके बाद after that each vertex of G1 is connected with each vertex of G2. You can see that each vertex of G1 is connected with each vertex of G2. Here you can see that four vertices. In our example we have 1 2 3 4 vertices, so there are 4 edges, 1 2 3 4 1 2 3 4 and so on. You can count and further see each edge of G1, each vertex of G1 is connected or adjacent with each vertex of G2. So this is an example, some properties of join of two graphs. The order of the join is given as order of G plus order of H. From the definition we can easily find that the order is given by this, and the size is given by this, because all the edges of G1 are taken and all the edges of H graph is taken, plus here I think here we have a mistake. This must be vertex set of G, because each vertex of G is adjacent with each vertex of H, so there must be order must be multiplied. So this will be our edge size. This is a size of join of a graph. Okay, so now what will be the degree of vertex in join of a graph? What will be the degree of a vertex in join of a graph? We can see that if a vertex belong to G, then the original then the degree of V in G plus the order of the graph or H, because v must be adjacent to every vertex of H. So the order of H times increase the degree of V, and if V belong to the vertex set of H, then degree of V in H plus order of G. And this is directly from the definition of the sum of the graph. So this lemma or this result, we will use this result. Please remember this result, because we are going to use this result in our next slides to obtain the degree based topological indices of sum of two graphs. Here we will discuss the first reformulated Zagreb index of sum of graphs. First reformulated Zagreb index. The definition of the first reformulated Zagreb index is given as here. Notice that we have now three types of edges. First type of edges, when both ends are in G. Second type of edges, when both ends are in H. And third type of edges, when one end is in G and the second end is in H. So in join of graph we have three types of edges. So we break the summation according to 1 to 3 types of graph, and here we apply the formulas which we discussed in our previous slide. For this one, when both vertices are belong to H set of G, then degree of U plus degree of V minus, this is as it is, and 2 times order of H. And I move to back slide for further explanation. If both vertices are belong to the vertex set, vertex set of this, then the first expression will be degree of G U plus degree of G U plus 2 times, because one from U and one from V, we have 2 times order of H. So this was the explanation for this one. And for when both vertices are from H, we have this value, and when both vertices are and one vertex is from the graph G and other vertex is from the graph H, we have this expression. Here we just put the values which we discussed in our previous slides. Okay, so we will we have now 3 terms, 1 2 3. We will discuss these terms separately because they are somehow lengthy computation, so I don't want to confuse you by taking in this all these in one step. So first we will discuss case 1, and the second case will be similar to as case 1, and after that we will discuss the case 3 separately, and finally we will add the results of 1 2 and 3 to obtain the final formula of the first reformulated Zagreb index of sum of graphs. So first discuss what is the what will be the value of the case 1. Okay, so let's move to the next slide to discuss this. So this is our first term, as I mentioned. This will be equal to, here we choose, this will be our A, this is our B. So we apply the formula of A square plus B square, A square plus B square, and this is our 2AB. Simple computation. And further, if you observe that if we apply the summation on this, you can see that this is exactly the first reformulated Zagreb index of our graph G when we apply the summation here, and when we apply the summation on this term, we get 4 is a constant, V of H is also a constant, so there is nothing variable, so we just multiply by the size of the graph G. And here if I remove this, now we have last one, 4 into degree of U plus degree of V minus 2. We expand it, and you can see that if we apply the summation here, you can see this is exactly 4 times order of h multiplied by first Zagreb index. So this is actually the first Zagreb index, and after that if we multiply 4 minus 2, we have minus 8 here, and this order of h is a constant, so order of h is as it is, and here we have, I think, yes, again type of mistake, here we have h because our summation is on h base. So this is the summarized form of our first term. Exactly on similar lines we can obtain the result summarized form of our second term. Just replace g by h, here h, here g, and so on, because the first term and the second term are similar except the graph g and h. So this is the results of our first and second term. Now we will go to the third term, which is somehow a lengthy one. So here we have our third term, degree of u plus degree of v minus 2 plus order of g plus order of h whole square. First, what we do, this is our a, b, c, d, e, and so on. We just open the square, lengthy calculation or computation. Here this is from here to here, we open the square, and after applying summation on this square, you can see that if we apply summation on this one, please focus on this. This is, you can see here we have g and here we have g. If u belong to the graph g, then this summation will give us m1 of g when we apply summation with respect to graph g. So this is our first Zagreb index, and when we now that we have two summation here, and when we apply summation from graph h, because in this there is no term of h. Okay, just I remove, and I again told you that you can see here is no term of from the graph h. So for this summation, this will be constant times m1 of h, like order of h multiplied by m1 of h. Similarly for this one, you can see here we have vertex from graph h, v is from h, so this is m1 of a graph h multiplied by the order of the graph g. And further, similarly, we apply this summation one by one on each term, and we obtain this long computation. So we simplified our first term, our second term, and our third term. So in finally we will add the result. I mean adding, you can see adding the result of terms 1, 2, and 3. We have the final or summarized form here, but a long one. The first reformulated Zagreb index of g plus h is given by this long expression. Of course, these are this expression is long, but useful if we have some very complex network that we can obtain from g plus h. You can see that in our first or second slide I said that if g plus 1 is a complicated network, then then by using the properties of our basic graph, like if we know the first reformulated Zagreb index of g, first reformulated Zagreb index of h, and order and size, we can find easily the first reformulated Zagreb index of g plus h. इसका मकसद ये होता है कि ऑपरेशन का, जिस तरह हमने पहली या दूसरी स्लाइड में बताया था कि हमारे पास कोई बहुत बड़ा, बहुत कॉम्प्लिकेटेड किस्म का नेटवर्क है, हमने उसका टोपोलॉजिकल इंडेक्स जो है वो फाइंड करना है, और हमारे लिए उसको ग्राफ की मदद से देख के काफ़ी बड़ा या मुश्किल होगा। तो हम क्या करते हैं, अगर हमारे पास कोई ऐसा ऑपरेशन है तो हम ऑपरेशन को यूज़ कर सकते हैं अपने बेसिक ग्राफ या छोटे ग्राफ की मदद से उसका इंडेक्स जो है वो फाइंड करने के लिए। जैसे कि आप देख सकते हैं कि हमने यहाँ पे अपना जो सारा एक्सप्रेशन है, ये हमारा जो है वो g और h की प्रॉपर्टीज़ की मदद से हम g प्लस h का जो फर्स्ट रिफॉर्मेट जो है वो ज़ैग्रेब इंडेक्स फाइंड कर सकते हैं। ये हमारा रिजल्ट था, फर्स्ट रिफॉर्मेटेड ज़ैग्रेब इंडेक्स फॉर जॉइन ऑफ अ ग्राफ For your exercises, investigate the first and second Zagreb index in Zagreb indices. Of course, first reformulated Zagreb index was a little complicated to compute, so that's why I choose first reformulated Zagreb index. And you have some easy tasks to compute the first and second Zagreb index for the join of graphs. I hope this is our, I think, last slide. Yes, we have some references here. You can see further explanation or further graph operation in these references. Yes, these are some references. Of course, if you Google about topological analysis of graph operation, you will see many more paper on this topic. So that's all from my side for this lecture. I hope you will try to solve some exercise, and if you have some question, you can discuss further your queries on your in comments and in class also. I will end with I will end the lecture by saying that this is the first part of graph operation. I think I will go 2 or 3 lecture, I mean 1 or 2 or lecture to explain this topic widely. नेक्स्ट हम सम डिस्टेंस बेस्ड टोपोलॉजिकल एनालिसिस है, हम उनके ऊपर भी बात करेंगे, और हमारा जो फाइनली हम ये भी बताएंगे कि इसकी एप्लीकेशन एग्जैक्टली कहाँ पे है. ठीक है, तो हम इंशाल्लाह जब हम डिग्री और डिस्टेंस बेस्ड इंडिसेस को डिस्कस कर लेंगे, देन वी विल गो to the application of graph operations and topological indices. Anyway, from right now, this is all, and best of luck for your lecture. See you. Bye bye. Allah Hafiz.